Okay, I'm just going to describe a couple problems here from your chapter. We're in chapter 12, problem 19, a biological application, where we have a person who is going to lay down on a board, and there's a little scale over here that has some numbers on it, and this person's going to lay down, and we're going to try to figure out where the center of mass of this person is. The way that they do that is they put this on here. They know the distance from the fulcrum point here to the scale is 2 meters. I think it says it's 2.00 meters. And it says that the student that is chosen to lie down on this particular board has a mass of 70 kilograms, which is awfully light for an adult, but that's all right. The scale has a reading of 250 newtons, and it wants to know where is the center of mass of this person, right? And this is 250 newtons beyond what the board is, and so we basically can ignore the weight due to the board, I believe is what it's trying to indicate that by that statement. So what happens? We have this board that's laying on this fulcrum point and also on the scale. When the person lays down, it's not clear what their actual weight reading is going to be on this. We can do a quick estimate and see that the weight of this person is probably something like that's mass times gravity, so something closer to 700 newtons. So their force should be something like 700 newtons, but the force scale here is only reading 250 newtons. And that seems perhaps a little bit inconsistent, right? I mean, where is all of that weight? Well, the center of mass, we can treat all of this weight as acting at the center of mass of this person. So in the relative scheme of things, where is most of your weight? We don't really know, right? I might have a guess that might be different than yours, but we don't even need to be precise about where that is. We'll just draw it at some point here. Because we can act as if all of the force from their weight is acting at their center of mass down. There's a fulcrum here that's obviously pushing up with some force as well. If it wasn't pushing up with some force, there'd be an angular acceleration in this direction. So what can we do? We can determine the net torque acting about this fulcrum, this little point here, and by figuring out what the distance is to the center of mass, which we don't know. And we know the distance to this force. We know that this force here, this is a scale, is actually, the force on the board is a force pushing up, right? We know that the weight, that the reading on the scale is due to the weight pushing down, but the force that the scale feels, is 250 newtons. So that's its force pushing, that it is forcing it to push back up with. And we don't really know what the force on the fulcrum is. So we want to choose a convenient point that makes this problem easy to calculate. What point would that be? Well, we know information about where this is relative to the fulcrum, and we know its force. We know the force here, it's this person's weight. We don't know the distance, but we don't know really anything about this force right here. So that's kind of our clue to calculate the net torque about the fulcrum, about this point, the pivot point. Because we don't know anything about its force. We don't know anything about its magnitude of its force, and we have a lot of other information. And what we're really interested in, we want to know this value of x, so that's going to be really important to us. So let's write out the net torques, right? We're going to write out the torque due to the scale plus, let's write plus for now. We're going to sum up all these things without talking about their direction quite yet. So the torque due to the scale plus the torque due to the weight. All right, and now for each of these terms, we need to determine the lever arm, the vector product of the lever arm and the force. All right, hope that's clear on there. So what is that going to be? For the scale, the lever arm is the distance from the point, the axis of rotation, all the way to where the scale is. Right? What is that distance? That's the distance of 2 meters. Okay, so that's the length of the board, which is equal to 2 meters. And we're going to take that, we take that magnitude times the magnitude of the force, which is 250 newtons. That's the force of the scale. times the sine of the angle between it. Well, the angle between these two happens to be 90 degrees. Okay, and that is moving kind of in the positive direction. We take r cross f, and that's going to come out of the page. So we'll call that a positive value. And the other one is going to be our r in the same direction cross f downward. That's going to be in the opposite direction. So we're going to put a minus sign in front of the torque due to the weight. Right? Its lever arm is some distance x that we don't know, the distance from the fulcrum to here. Right? We know that value is going to be less than 2 meters, which would be a useful check when we come around to it, times its force, which is the weight, right? The weight of the person, which is the person's mass times gravity, times the angle between them. And again, this angle in this particular case happens to be at 90 degrees, but it certainly doesn't need to be. In a lot of the problems you have for homework, that's not going to be the case. So each of these numbers, these values here, calculates out to 1. We know, because this is in static equilibrium, that the sum of these is going to be equal to 0. That's what static equilibrium means, the sum of the torques equals 0. And now we know what the length of the board is, we know what the force on the scale is, we know what the weight of the person is, and we simply just don't know the distance. So we can solve all of these out. And if you can bear with me just a second, I might be able to just do these. Mostly the length of the board is 2 meters, the scale is 250 newtons, minus the mass, which we'll just take to be 700 newtons, mass times gravity, times x equal to 0. So this is going to be equal to, we add this number to both sides, so this is going to be 500 Newton meters on the left divided by 700 newtons equal to x. Right? So the newtons cancel out, we get some number with units of just meters, because our newtons are going to cancel, and it's 5/7, whatever that is, right? So 5/7 of a meter. And let's see, so my initial actual intuition, I didn't really say anything about it, my initial intuition was that the center of mass would be closer than the midpoint. It wouldn't be around the hips or anything like that, because we have our whole entire torso, plus our arms, plus our head, which is actually quite heavy, and especially mine. So that seems consistent, right? At 1 meter, it would be exactly in the middle of our body, but at 5/7 of a meter, that's the distance, and we measured that as x, right? We said x is 5/7, which means it would be closer to the fulcrum point. The question itself actually asks determine the location relative to the feet. So relative to the feet, this is simply 2 meters minus 5/7, or 9/7 of a meter, right? It's going to be closer to the chest area, right? We just simply have more mass in that particular area. So hopefully you can see the similarities between this and some of the problems you have for your homework assignments, where the angles might be different, but we need to be mindful of what the angles are, what the forces are, and what the lever arms are for each case.